We want to look now at the concept of finding volumes using integration. And really what this is about is the idea is if we take a curve and we rotate it around an axis. So in this case we're going to do the x-axis first, but you could rotate it around the y-axis. You're going to get a particular shape. Now depending on the curve, the shape would be different. And this will really mimic things that exist in real life. And we can, things from real life, if we take them, we can model those in regards to mathematics and actually find the volumes that you need. So the idea is what we're going to do is take this line, rotate around. So this area between 0 and 1 here is going to get rotated around the x-axis. So we're going to get a shape that looks like that, and it's going to look like a cone. Whereas it's just a line, it just goes around, and the area gets swept out and encompasses the volume there. So the cone has a line, there's our line, y is equal to 3x. And what we want to do here is work out the volume of the cone. So we're going to use integration. We could find the volume of a cone, obviously, by using the volume, the formula for the volume of a cone, 1/3 times pi r squared times the height. That's quite fine to do with a cone, but we're going to use this one as an example of how this is done using integration. So the idea about in regards to the integration is actually taking a slice of this cone. Now, if we take a slice, it's really going to look like a cylinder. So it's going to be pretty much a cylinder. So the volume of a cylinder, well, it says volume of the circle, it really should be volume of the cylinder, is the area of the circle, which is the blue part, times the thickness in the yellow part there. Now if we work out the volume there, we need the area of the circle, which is we need the radius before that. So that's going to give us the radius of y, because if you look at your diagram, any point along here is going to be the y value. So we go across x, we go up y in our function here. So it's going to be a radius of y. So the area of the circle is pi y squared. The thickness is dx, or delta x, whichever we'd like to call. We call dx in this case. But the idea is that there's a change in our thickness. So it's similar to what we talked about with the idea of the integration, when we try and get the thickness as small as possible, and that means the more cylinders we would have. So the more cylinders we have, the better our actual volume would be. So the idea is that we take the volume to generate the volume here. We take our curve y is equal to 3x between 0 and 1 and sum the volumes of those individual slices. That's really the same as finding the integral here, which is from 0 to 1 of pi y squared dx. Now if we look here, this gives us a little bit of a problem, because we've got a function y, but we want to integrate with respect to x. So if we look at our function there, y squared, we need to change y into 3x. Now we know that y is equal to 3x because that's our function. So y needs to be put in terms of x. Otherwise, we're going to have troubles because we can't integrate with respect to y. Remember, we're told what we need to integrate with respect to, and we have to change our function, and there's the trick there. That means we got 9 pi x squared, because that gives us 9x squared. Now we can integrate it. So we add 1 to the power, we divide by the power, and we're going between 0 and 1. So the 3's would cancel with the 9 to give us 3 there, and so we get 3x cubed. Substitute 1 in, substitute 0, just leaves us with 3 pi units cubed. Now you can check that, because it's a cone, you can check that you get the same volume, and you will see that it would be 3 pi. So let's have a look. This will give us something what we call a truncated cone, because the end would be cut off. So we're going between this area here, between the x-axis, x is x plus 1, the curve there, and 0 and 3 is rotated around the axis. So the volume so formed would be given to us by this. Remember, we're going to the idea that we've got volume being pi 0 to 3 of y squared dx. So we go back to that idea, y is equal to x plus 1, so it's an easy substitution for y to x plus 1. So we add 1 to the power, we divide by the power, we haven't put the 1 in, but we could, because it's 1 in front of the x. So we get pi outside of and we can just leave it out there. Because it's a constant, it doesn't change. So you can leave it out there. Substitute 3 in, substitute 0 in. Just be careful with this one, because it's 0 plus 1, it doesn't make the whole thing 0. Common errors would be, we get used to subbing in 0 and the whole thing 0, not in this case. So if we do that calculation, we get 21 pi. So keep going back to the idea that we're basically summing a whole lot of cylinders, and that's what the integration is about. That's where the pi y squared comes from, because that's the area of the circle times the thickness is our cylinder, and then we're doing the sum of all the cylinders between our values there.